Yeah, we were discussing various errors associated with the operation amplifier. In the previous lecture, we had discussed about bias current introduced error, and we had also explained that with several examples. In this class, we will discuss about gain error. So, the gain error is an important component in error budgeting. So, we discuss this in detail. So, gain error in operation amplifier. Because we had seen that to operate the operation amplifier with certain amount of gain, for example, if I want to gain 10, so we merely put the two resistance with the ratio of 1:10, then for example I have 1k and 10k, then you get the gain of basically -10. But this is only an approximation, and with this if we start designing the circuit, then soon we will find that our circuit is not accurate enough, and we get into very many problems. That is what we will going to see this one. So, in actual case this gain is not really is equal to 10. This is the thing that we want to point out, and then what is the effect of this in the circuit applications and how to correct that. That is what we will see in this. So, we will fix this one in two parts, that is actual gain and then the set gain. Set gain is that our RF by R1, that is this RF and that is R1. So, that is the set gain, but what is the actual gain, that is the question, because operation amplifier is not giving the gain which is equal to RF by R1. For example, 10k and 1k if I put and then give the here 1 volt, I expect it to get -10 volt, but in reality you are not going to get -10 volt. This is going to be different, and that difference matters in most of the cases. So, that is our worry, and then our intention here is that how much is the difference and how to reduce that error, and then we work out few examples. So, the significance of this error. So, we will see this one in this class. So, actual gain, set gain is not equal to actual gain. So, this problem is to be solved. Now, one may wonder where from this error had come. Now, this error actually had come from our basic assumption that if you see our actual circuit, that what we have made, that we have taken this, for example, in actual deriving this equation, we have taken, for example, the input voltage is given here, and then we have connected this to ground. So, we assume that this is 0 and then this is 0 and you have Vi, and then this is R1 RF. So, we will assume the inverting inverting terminal voltage is equal to non-inverting terminal voltage. But this is not really true, but this is not really true, because if I assume that if the inverting terminal is 0, the non-inverting terminal is 0, then we assume this is also 0, but then the output of the operation amplifier is actually if we take it V0, this V0 is coming from the difference between these two only, because the difference between the two inputs only amplified by the operation amplifier and put it at the output. So, in actual use, in actual case voltage difference between non-inverting and inverting terminal is amplified by open loop gain. Other way around, V0 is actually nothing but V0 V plus minus V minus into open loop gain, which essentially means if V0 is some finite value, then this cannot be 0, because V0 is non-zero, So, this cannot be 0, that is V plus and V minus cannot be equal, there will be a difference. So, if you find the difference actually, that is V plus minus V minus, the difference between the two input terminals is nothing but V0 by A. We take A as open loop gain. So, A is coming as an open loop gain. This is an important difference that one have to understand, that the two input terminals are not exactly equal, there is a difference, and A is the open loop gain. Normally when open loop gain is very high, for example, even if we take 741, the lowest gain is 20,000. If its the gain is 20,000 and V0 is say for example 10 volt, for example for V0 is equal to 10 volt, for A is equal to 20,000, that is the minimum gain specified for 741. If I take that one, then you will get V plus minus V minus, the difference between the two will be equal to 10 divided by 20,000, which actually comes out to be 1 by 2000, which is equal to if we take in microvolts, then this is coming in volts. So, that is coming 0.5 millivolt. You will have a 0.5 millivolt difference will be there to produce a 10 volt output. That means these 2 points are not at the same potential. That is, if you look at the op-amp input now. So, if I ground this one, then if I keep 1 volt and then if I have 1k and 10k, then I expect nearly 10 volt, then this is 0, but then this is minus 10 volt. So, minus 10 volt to come, this is sitting at minus 0.5 millivolt. So, minus 0.5 millivolt is the difference now you have between these 2 points, and this 0.5 millivolts amplified by the open loop gain 20,000 is what appears at the output. Since see in our derivation we assume that this is also 0, this is also 0, but actually this is not 0, this is at 0.5 millivolt, that 0.5 millivolt. The net result is our gain, actual gain is not 10, but it will be less than 10, and the output also not going to be 10 volt, it will be little less than 10 volt. So, in actual case this will be little less than 10. This is because the voltage across this is R1, is not equal to VI. This is the main issue actually. So, the voltage across is not equal to input. So, this creates a error. So, how much error that it creates, and is it possible to write a general equation to find out what is the error equation, and then we also have to see how to apply this error equation in our design, because this factor has been forgotten by most of the designers today, and in actual practical world this has great implications while doing the error budgeting. So, one have to aware of this error, and then how to apply this also to be known. So, the net result is that your gain. So, the set gain and the actual gain are different. So, in fact, what really happens is actual gain is always less than set gain. Actual gain is always less than set gain. Actually, this is to be plus 0.5 millivolt, not minus, because this voltage as to output has to be minus, means this has to be plus. So, this voltage is plus 0.5 millivolt. So, if we see this, so the voltage across this resistance, we have 1 volt, and if this is sitting at plus 0.5 millivolt, then voltage across this is not 1 volt, voltage across this is 9.5 millivolt only instead of 1 volt, and this voltage only produce a current. So, originally we assume if it is 1 k, then 1 milliampere current is flowing. Now, it is not 1 milliampere, it is less than 1 milliampere. Same thing happens, the current flowing through is also less than 1 milliampere. The net result is voltage across this also less. That is why the actual gain is always less than the set gain. So, now we try to derive a general equation to find out what is the relation between the set gain and the actual gain. So, if I take that, then I will take this as 0 volt. So, then this is taken as instead of 0.5, take it as a general value as x. So, what I do is I will remove this and put this as x. It is not sitting at this is sitting at 0 and this is sitting at x, and take this as V 0, and then this is RF, and then so this is R1. So, you have a RF R1 and V input, this is we take it as V input, and that is V 0. So, the set gain is RF by R1. The actual gain is V 0 by V input, that is what we wanted actually. Now, if I take this as x, so if this is as x voltage, then the current through Ri can be computed. So, I can take the current through Ri as this is Vi. So, you have so we will have I put the circuit at this corner. So, I have as a Vi. So, we will have output as V 0. So, this voltage actually we can say Vi minus V 0 by A into RF by R1 is equal to V 0. This is coming mainly by this factor, because RF by R1 is your gain. So, I try to find out what is the voltage that we are applied here, it is Vi, and then we know voltage at this point is V 0 by A, that is your x. So, V 0 by A is equal to x that we have defined in this at this point. So, this is nothing but V 0 by A, because why x is V 0 by A? The reason is that if I have to get output voltage V 0 here, if I have to get V 0 here, then I need a difference between these 2 points, because the difference between the 2 points amplified by open loop gain is what we get as output. So, if I get V 0 here, V 0 by open loop gain is the difference that is expected here. So, the input difference equal to V 0 by A. That means this point is at V 0 by A, because this point is at V 0 by A. That is why V 0 by A into A gives you V 0 here. So, I have to take this as at V 0 by A. Once if it is V 0 by A, then we have to take the applied voltage is not actually, if we go by our earlier formula, applied voltage is taken as V I and multiplied by the gain. Now, applied voltage is not V I, it is less by V 0 by A. So, we have take the applied voltage V 0 minus V I by A into R f by R 1 is our output voltage. So, the input, that means the effective input voltage, the effective input voltage is nothing but V I minus V 0 by A, which we are taking it as V I. So, that is why that the effective input voltage V I minus V 0 by A into gain set, that is R f by R 1 gain set is equal to V 0. Now, we have to now simplify this to get the form that we want, because we have to get the actual gain that actually is required. So, we will simplify this by taking A, multiplying this A. So, V I into A minus V 0 into G S actually gives you divided by, you have divided by A, that gives you your V naught. Now, we can write the actual gain V 0 V I as a actual gain. So, V 0 by V I can be written as actual gain, that is equal to gain A. So, if I simplify this equation, so you will get A minus, because we can divide this by, okay, we can simplify this here itself. So, I can get V I minus V 0 by A into G S comes as V naught. Now, I can write this 1 minus, or I can write A into V I minus V 0 into G S equal to V 0 into A. If I divide both sides by V I, then I will get A into G actual gain, because we can write V I, okay, A minus, that actually appear as A minus, we will get V 0 by V I here. So, that will come G S, that is actually G A I write in two different form. So, divided by A, I will get V 0 V I. So, you will get G S minus V 0 by V I into A. I merely divided by V I. So, just divide this by V I, you will get this. So, I divide all the terms by V I, then that is what it comes. So, we can now put V 0 by V I as actual gain. So, A minus G actual into G S actually comes G actual into A. So, now if we can simplify this, that appears as G S set gain is actually G A divided by into A, then you get A minus G A. that on simplification you will end up. So, Gs actually comes as you get Ga divided by 1 minus Ga by A. Now, we get into the next page. So, we will get up the set gain is actually equal to actual gain divided by 1 minus Ga by A. This is an important relationship. For example, if I have take for example typical op amp of I want 100 gain, then if Gs is equal to 100, then what is Ga? Assume A is equal to 10,000, open loop gain is 10,000, then you will get the set gain 100 is actually Ga, that is what we have to get, that comes 1 minus 100 divided by 10,000. Actually C is Ga actually here is not 100, we are applying in this. So, you get Ga by 100. So, if I multiply this, you will get 100, 1 minus Ga by 10,000 gives you Ga. So, that makes for example 100 minus Ga by 100 gives you the actual gain. So, if I see this one, this comes the actual gain as 10,000 minus Ga, that comes 100 Ga. So, 10,000 comes as 101 Ga. So, you get actual gain would be 10,000 divided by 101, which will be close to 99. So, instead of getting 100 gain, we are getting only 99 gain. So, the actual gain is actually little less. Now, the gain if it is little less than 100, it is not a serious issue, but the actual problem comes not because of the small reduction in gain. This 99 gain, is it stable? The gain 99 is not stable, that is the main issue, that is what we are going to explore now. So, the first step that what we have done is that the set gain 100, that we are not really getting it as 100, the set actual gain what we get is actually less than 100, and that relation is actually given by this equation. So, the this equation defines what is the relation between actual gain and set gain. Now, the difference between actual gain and set gain will be more if the open loop gain is less. For example, if the open loop gain A is very large, then this term become negligible, and then you will get set gain is equal to actual gain. But then this will be negligible only when A is much larger than actual gain, that what you are going to get. So, if the open loop gain of the op amp is very large, then set gain and actual gain will be small. Now, one has to remember that A, that is the open loop gain, is not a constant factor for a given op amp, it changes with temperature. This is the main issue in actual case. So, if the gain has to be stable in the op amp, that means if the set gain and actual gain, set gain and actual gain are to be close, close enough, then open loop gain should be very large. Open loop gain must be very large. So, that is one condition. So, first condition is that open loop gain should be very large. Must be large compared to set gain. other way around, we should have only less gain to be set from the op amp. And then the second point is, if the open loop gain A changes with temperature. For example, higher the temperature, the open loop gain be higher. So, for a given op amp, if the open loop gain changes, then the actual gain also changes, even though we are not changing the set gain. So, the gain of the gain provided by the gain obtained from the op amp changes with the temperature. Now, this is a very important point that we have realized, that is, whatever gain that we are getting, that is not constant, that changes with the temperature. This is because A is changing with the temperature, because open loop gain A changes with temperature. So, if that means the gain that what we are getting actually changes with temperature. Now, our aim is we want to minimize the change. That means, if the ratio, that is our ratio between the set gain and the open loop gain is very small, then the change also will be very small. So, if to keep the gain change minimum, to keep the gain change to a minimum amount, to a minimum we have to make sure set gain by A is small. That means, one should not try to get large gain in one single op amp. That is the thing that we have to remember. Now, let us work out one or two examples to illustrate this point. So, for example, example 1 we take. For example, in this case, we want to have a gain of 1000. Suppose assume the required gain is 1000. So, the required gain is required gain is 1000. Assume we use a op amp 741, the A is equal to minimum 20,000 for 741. So, A is 20,000 and the required gain is 1000, that is we call it as what we get is a set gain, we want set gain as 1000. So, if I take this, then we will put, for example, to get a gain 1000, what I do is I will put this, assume I keep here 1 meg and then 1 k and my signal is given here. So, the gain the set gain is 1000 is there. Now, will I get the actual gain 1000 or how much I will get, and what will be the effect of temperature for this, and then we will show the second example, that if I modify the circuit, then the error that I am going to get will be very small. So, now for this let us work out the gain error. So, if I calculate the gain error, for example, this set gain in this case is 1000. So, you have 1000, that actually I do not know what is the actual gain. So, I put this divided by 1 minus Ga by 20,000, that is what actually it comes. So, the actual gain would be, so the So you will have actually even this formula can be rewritten in the following way, that is we can also show in the derivation that actual gain, because this we are written in terms of set gain, I can also write in terms of actual gain 1 plus Gs by A. So, this is also this equation also can be derived from this equation. There is no problem that you can rearrange the terms, then you will get it in this form. So, actual gain that you get will be in terms of set gain one can obtain. So, if I apply this equation, if I apply these quantities in this equation, then you will get for example, actual gain would be, I want a gain of 1000, then I have 1000 plus 1 plus 1000 divided by 20,000. So, this actual gain that you get would be, this is the set gain, this is the open loop gain. So, you will get 1000 divided by 1 plus 1 by 20, which actually works out to be 1000 divided by 1.05. So, so that actually will come, the gain will be actually roughly by actually if you take this you will get 9 times. So, 945. So, you will get 55 into 0. So, that will come 5 times. So, you will get around 95.5, you will get the gain. So, actual gain is not 100, but it is actually only 95.5. Now, this had happened because we had tried to get large gain here. If the gain is, if I put lower gain here, but set gain is lower, for example 10, then the gain error will be small. As I increase the gain more and more, my gain error increased. Now, this as such having a lower gain than what we wanted is not a serious issue. If I want 100 gain, then I can put 105 and get the required gain of 100. But the question is whether this gain 95, what is there, is it constant, is it steady? The question is it stable, is it stable against temperature? That is the question actually. Is it stable against temperature? Actually, this is not stable. When the gain changes, this also changes. For example, assume that op-amp open loop gain increased to instead of 20,000, the open loop gain changes with the temperature. So, assume because in all the cases the gain open loop gain of the op-amp changes with temperature. So, the open loop gain, the open loop gain of the op-amp changes with temperature. So, for example, assume that the gain increased from 20,000 to 30,000. Then if I calculate the gain, then the new actual gain would be, is given by, so you will have the that gain set divided by 1 plus gain set divided by A. If you apply this, then we will apply this now. So, you will get here, this is 1000. Now, 1 plus 1000 divided by 30,000. Now this works out to be, that actually works out, actual gain would be 1000 divided by 1 plus 1 by 30, that comes 1000 divided by 1.03. So we had actually 1.05 there, and that actually it become 1.03. Now if you calculate this, there will be a 3% decrease, and you will have that the actual gain would be 97, around 97 you will get. So earlier it was 95, now the gain had become 97. That means at for example, if the op-amp temperature changes, the room temperature changes, then the gain shifted from 95 to 97. So for this that is uh, so the actually this 970, sorry, this becomes 970, it becomes 970. Okay, here also this is to be 955, actual gain would be 955. So the gain supposed to be 1000 had become only 955 in this case, and then the gain supposed to be 1000 here had become 970. That means the gain had drifted from 955 to 970. So actually uh, the gain which is supposed to be 1000, which is supposed to be 1000 is at 25 degree, for example 25 degree C ambient, it had become 955. At for example 80 degree ambient, it had become 970. That is, the gain is actually changing with the temperature. This problem, this looks like non-trivial, but actually it is a serious problem in circuit design, which is not understood by many of the designers. So you have the gain of the op amp. First of all, if you set 1000, it is not going to be 1000. This will be something different actually, and that also changes with temperature. Now, what is the expected problem because of this? Now, this gives a problem because, for example, if I want to amplify some signal, for example, I want to amplify thermocouple voltage. So, I have a thermocouple amplifier, for example, I put this, I have a thermocouple voltage is given here, single junction thermocouple. So, take for example, thermocouple amplifier. Take this as an example 2. Take thermocouple amplifier and then assume that this gives you 40 microvolt per degree C. If I give for example gain is equal to 1000, that is I set the gain as 1000, then what I wanted here is actually 40 millivolt per degree C. So, every 1 degree difference in temperature will produce 40 microvolt here, and if I give a 1000 gain, then I will expect 40 millivolt at this point. So, for 100 degree change, then for 100 degree room temperature, for if this temperature for the junction temperature of 100 degree junction temperature, to avoid confusion, if you want, you can also have two junctions, and one at 0 degree C, one at 100 degree C. So, I can put it two junction also. Those who are not familiar need not worry about single junction thermocouple. For example, if this is at 0 degree C and if this is 100 degree C, then the difference is 100 degree C. So, for junction temperature difference of temperature difference of 100 degrees C. See, the expected voltage is the expected thermocouple voltages voltages 40 into 100, that is equal to 4 millivolt. So, we expect it the 1000 gain. So, it will be, so for gain of 1000 set gain of 1000, the expected output voltage voltage is actually 4 millivolt into 1000, that is equal to 4 volt. So, the expected voltage is 4 volt, but what actually happens is when the but we know that we had shown that if it is a 741 and a gain of 20,000 at room temperature, then the open loop gain of the 741 actually actually goes up to 30,000 at 80 degrees C. So, at when the open loop gain is 20,000, then the gain will be 955, and when the temperature goes high, that 80 degree, the gain goes to 30,000, then the actual gain increases to 970. So, that means at 25 degrees C. So, when the but in real life, but in real case you will never get 4 volt output, but even though thermocouple voltage is correctly at 4 millivolt. At 25 degrees C, we know at 25 degrees C, ambient, the A is equal to 20,000. At 85 degrees C, 80 degrees C ambient, A is equal to 30,000. This makes from our earlier calculation that set gain, the actual gain at 25 degrees C ambient is 955. Actual gain at 80 degree ambient is equal to 970. That means output V0 at 25 degree C ambient would be 4 into 955 millivolt. V0 at 80 degree ambient would be 4 into 970 millivolt, which actually means it appears as if as the ambient temperature increases, the output voltage also increases. That is what it means. That is, this is the voltage that you get, that if you calculate this at 25 degree C, it comes out to be at 25 degree C, that comes out 3.82 volts, 82 volts. At 80 degree C, it turns out you have 3.8 volts. So, we see the difference of 60 millivolt, difference in output is equal to 60 millivolt, because this is 3.820, this is 3.8 volt. That means the output voltage drifted by 60 millivolt for the ambient temperature change of 25, change from 25 to 80 degree, that is 55 degree change created 60 millivolt change at the output. But at the output we know 4 millivolt is 1 degree C, because at the output we have 1000 gain, at the input is 40 microvolt is 1 degree C, at the output of the op amp 4 millivolt is 1 degree C. So, at the output of the op amp, sensitivity is equal to, sensitivity is actually equal to 40 into 1000 microvolt, because 1000 is the gain. So, that comes 40 millivolt, sorry. So, it is actually 40 millivolt comes as a 40 millivolt is coming as a 1 degree C at the output. Actually, we have 4 millivolt here, 4 millivolt into 1000 actually comes 4 volt, instead of 4 millivolt, which is actually 100 degree C, which supposed to come 4 volt, we first of all got only 3.82, and that too that increased it to 3.80, that is 60 millivolt increase, that is 1.5 degree error had come at the output. So, the error, the expected temperature drift, expected error is equal to 1.5 degree C at the output. So, this error had come purely because of gain drift, and if you calculate the total error, that is, this is only change in error, but if I take the real error, for example, at this point of 4 volt you are getting only 3.82 volt. So, in terms of absolute error, so the absolute error is only a difference error of 1.5 degree, the absolute error would be, the absolute error at 25 degree C would be 4 minus 3.820 volt. That is 180 millivolt. So, 180 millivolt, that is equal to 180 divided by 40, that is 4.5 degree error. So, absolute error is high, and with temperature that it is changing, and that error is 1.5 degree, that difference error is 1.5 degree. So, that means if I try to use the op amp and I had put 2 resistors to get a gain 1000, and I have not got the gain 1000, and in that case instead of showing 100 degree C, that it will be showing only much less than 100 degree, that is less by 4.5 degree C, that is it will show only 95.5 degree C, the 100 degree temperature will be shown as 95.5 degree, and that too with when ambient temperature changes, that will change to 97 degree. So, at room temperature, 100 degree C temperature will be read as 96.5 degree C, because you will have 4.5 degree error at room temperature. At 80 degree C room temperature, or 80 degree C room temperature, 100 degree C temperature of the thermocouple will be read as 1.5 degree will be added up, that will be actually you will have 3.120. So, 120 will be 3 degree away. So, that will be 98 degree actually, this will be 4.5 degree error, 400 minus 4.5, at add 1.5, that will come as 98. So, if I add this one, it will show as 98 degrees C. So, first of all the temperature is wrong, and it also, the reading also changes with the ambient temperature. Now, that is actually coming because I think there is a mistake in this calculation. Okay. So, we have one, this difference is actually coming as 820 60 is 1.5 degree error is coming. So, nevertheless that you see that temperature changes with ambient temperature change. So, this had come because the op amp gain is changing. If you do not want this to be this to happen, then one easiest way is do not get all the 100 gain in one single stage, get the required gain in multiple stages. So, the what is to be done? So, what is to be done? Obtain the required gain, obtain the required gain of 1000, in 3 stages, instead of in one single stage. Then you will find that the gain drift also less, the gain error also less. For example, what you can do is that I can have gain 1000 in 3 stages. For example, I can have the input like this and have only 10 gain in the first stage, then I put the next 10 gain in the second stage, and then another 10 gain in third stage. For example, I can even use so I assume I have gain 10 here, and then gain 10 here. So, we have 3 stages. So, total gain is 1000. Total gain is 1000. Now, if we calculate the V0 and V input, you will find that gain error is much smaller, because the single stage gain, if I calculate the single stage gain, if I calculate, so actual gain would be that is set gain of 10 divided by 1 plus 10 by 20,000. So, that actually works out to be 10 divided by 1 plus 1 by 2000, which works out, you will have 10 divided by 1 plus 1 by 20,000, that comes at 0.005, actually 0.005, which will come as 1.005. You will find this gain is coming very close to 10, that will come, you will find 9.995. You have to work out and see what is the actual value that it is coming. So, you will then, if you multiply this by 3 stages, each stage will have this, and then for 3 stages total gain would be we have to multiply by, that is 10 divided by 1.0005 into 10 divided by 1.005 into 10 divided by 1.005. Now, if you calculate this, that you will get almost 999, close to that you will be getting. So, now the gain error is much smaller compared to what we had in the earlier case. So, by getting a lower gain in single stage, the gain error comes down and the drift of the gain with temperature also will be less. For example, if I try to find total gain at 80 degree C, 80 degree C ambient, that would be 10 divided by, you will find that 1 plus 10 divided by 30,000 into the 10 divided, because 30,000 is the open loop gain, then you will get again same thing 10 divided by 30,000 plus into 10 divided by 1 plus 10 divided by 30,000. You will find that this is also coming very close to this, you will get 99.5. I have not calculated this, you check this, but you will find that the difference in gain is only very small. So, we will find that with the temperature gain is not changing much. So, it is a better option to have higher gain obtained from many stages rather than a single stage. That will make the gain error also small and the gain change also very small. So, the what is required is to get larger gain, use many stages, that is obtain the gain from several stages, smaller gain from several stages, that is get the required gain, from multiple stages. This reduces the gain error and also gain drift. That is why one should not get try to get large gain on single stage itself. If you get a large gain, then you will have gain drift as well as gain error. So, the advice is do not get large gain, do not set large gain, for one single stage or one single stage. This is the thing that we have to remember. If you do not set large gain, if we get if we set a smaller gain, and if you want large gain, get it from several stages, then the gain error and the gain drift error also will be less. So, with this I will stop this lecture. Thank you.